your life.
Yeah.
Yeah, you can start.
Okay. Okay. So let's continue our discussion. Most likely this will be the last lecture on interactive proofs. So while dealing with interactive proofs, we saw this is a new model of computation, new model in which you can interact with the prover. And we saw that you can do certain things like, for example, graph non-isomorphism, for which we did not have a short NP proof. You could have an interactive proof. Then we saw that actually all of not just graph non-isomorphism, in fact, all of these space can have this one. But a special property of some of these proofs was the fact that these were actually public coin interactive proofs. And what does this mean? This means that at every step, the verifier does not do anything, but just tosses coins and hands over those coins to the prover. The verifier is actually extremely dummy verifier. It doesn't do any computation. It just tosses coins, hands over the coins to the prover. Tosses coins, hands over to the prover. And at the very last step, based on all the answers to the from the provers to various random questions, just does some polynomial time computation based on all these random things and decides to accept or reject. This was what a public coins interactive proof was. And we gave it a special name called Arthur-Merlin proofs. Arthur-Merlin means that they are public coins. And it's in particular called AMKN is one which has AMKN is exactly defined it to be set of all languages that L has a public coins IP protocol with at most KN rounds. Okay. And sometimes to be a bit pedantic, I might use AMKN, and we might also use MAKN if Merlin, that is the prover, starts. Starts the protocol. So if the prover starts, I'll call it Merlin author. If author starts, if the verifier starts, I'll call it Arthur-Merlin. And we listed a bunch of properties of Arthur-Merlin proof systems last time. I'll list it again. But two special classes of them are what are AM, which is just AM1, and MA, which is MA1. That is, author speaks, or then Merlin responds, or Merlin sends, and then author does something. We'll refer to these two. This one. Just because these are important classes, let's actually go into detail. Let's unravel the definition and see what these objects mean.
So in one of the examples of MA was like the permanent thing, right? Or
so that is the permanent and PQBF are in MA or I. They are actually in AM poly. They are in MA poly N.
Yeah, because it's the prover directly sends
prover. Yeah, but if once you allow poly N, you can, it doesn't matter whether you call it MA or AM, because the first round you can assume the verifier sends something and it is not used at all. Yeah. If I care only for like 1 or 2 rounds there, if you really care whether the rounds is 1 or 2 or 3, then it matters whether who is the first speaker. If you're going to say poly N
is equal to MA AM poly.
Huh?
MA poly is equal to AM poly.
MA poly is AM poly. If you are willing to fudge the number of rounds by 1 or those, then AM or MA doesn't matter. In fact, that's why people never write MA poly. There's only one reason. So MA and AM are what are public coin interactive proofs with one round, and the only difference is who speaks first. So here it matters. So let's actually go a little more careful into the definition and stare at this. Who speaks first? So let's start with AM. So once again, AM is here in this setup in which you want to ask whether X is in the language or not. So there's a verifier, which I'll now call Arthur, and there's a prover, which is Merlin. And how does the protocol go? It's AM, so the author starts, he sends a message R. He sends a message R, then Merlin responds. Merlin responds, and then author based on X, MR, either accepts or rejects. That's how the entire, that's the protocol. It's just a one protocol. So let's see what is one. Firstly, this is a one round thing. Therefore, this object should be an efficient computation. And then you should have two things. One is completeness, which says X is in the language. Then when over the probabilities of R, the random coins of R, there exists an M. There exists an M such that A, X, M, R accept. I should write A, X, R, M. Respect the order in which they come. Accept should be greater than 2/3. And soundness says if X is not in L, then the probability over R that there exists an M such that AXRM equals accept should be less than or equal to 1. I've just unraveled. So this is, look at this, this is almost like NP, except there's an initial random. So the NP, the prover sends a proof and then the verifier verifies it. Here the prover waits till the verifier sends some random points and then the verifier, and then the prover sends the proof across. The first step is the verifier sending across some random points and then this one. So this is AM. And MA is a slight modification of this in which Merlin speaks first. So it goes like this. It's almost the same thing. X belongs to L. You want to ask this? A. Author. They both have this one. And it now here it starts off with Merlin speaking. He sends M across. Now author can toss the random points. He can give it to Merlin, but there's no point of giving it to Merlin. He just tosses some random point and then decides to accept or reject based on that. Because whether he gives the random points to Merlin or not, if there's no point of it, because Merlin has already committed to this message. In this case, it's almost the same thing. Its completeness states that there exists, if X is in the language, then X is in the language, then there exists one message Merlin such that Merlin can set that over the random points of this one, AX MR equals accept is greater than 2/3. So notice that this is more, and let's write soundness before I make any remarks. Soundness says if X is not in the language, then no matter which message Merlin sends, probability R AX MR equals accept is less than. Okay. Notice MA, if you notice, MA is exactly like NP, except that the deterministic verifier is replaced by a randomized verifier. Okay. Are people with me on the definitions of AM and MA? They are.
So whenever the Merlin guy sends in the M is also randomized, right, in some way?
No. Merlin sends a proof.
Okay.
He could be randomized, but there is X. If X is in the language, there is a proof. This is exactly like NP. There is a proof, except the way you verify the proof is now you use randomness to verify the proof. So notice that MA, there is no interaction between Merlin and author in the MA. The proof is written and then the prover can go away. There is no, the prover, Merlin does not have to, there is no communication going back and forth between them. Merlin just writes a proof on where he can write it on stone and walk away, and author just checks if only the checking process is randomized. The usual process in NP, the checking process is deterministic here, but the checking process is randomized.
Yeah.
Okay. I want to make a couple of small, this one, because we're going to talk about these classes. Notice that we recall BPP we had shown is in sigma 2p. That is a randomness step can be replaced by an existential quantifier. This is sort of stating a randomness quantifier is subsumed by an exists for all quantifier. Or because it's also in intersection pi to p, it's also for all exists. By the way, somebody is at the door, just give me a second, I will be back. Sorry. Okay. And if you look at this proof a little carefully, you can sort of use the same argument to say MA. You can put it in MA is the existential quantifier. There's an exists first, then author speaks. Author is a randomized guy, so you can replace it that exists for all. It's a randomized guy, which is a more convenient thing to do. I will actually replace it with exists for all, and this is equal to what we'll call, this is what we know as sigma 2p. So MA is in the same proof which we showed BPP is in sigma 2p. If you look at the proof, stare at it, you can show that MA is in sigma 2p. And AM, you can do the same thing. AM is, this will be in exists. So this is there exists. So the ideal thing to do will be for all exists. So this will be contained in pi 2. Okay. So MA is, can put this one. You can ask what is.
Could you go back to how you defined MA?
Yeah.
So there will be there exists M, and that thing is in BPP, the
Yes.
probabilistic thing. So that would
Yeah.
be there exists for every because of the sigma 2p.
Yes.
For the soundness, it would be for every.
No. It's always there exists M for exists for all. You have to. It's not soundness and completeness are not two separate things. They go hand in hand with each other. Here, the soundness is exactly the contrapositive of the.
Yeah. Okay.
Yeah. One second. Something has gone wrong with my.
Oh, I think because it's raining, the bell might have short circuit.
Yeah. Seems like that. Yeah.
Circuited. Let's see. Otherwise, I'll switch off that whole face. Okay. So MA is an AM. Now I want to compare MA versus AM. Actually, what we will show the following proposition, that MA is actually contained in AM. So basically, what do I mean? What do I want to say by this? You give me a protocol like this. Arthur-Merlin, in which M and then randomness. This I can convert such a protocol into X belongs to L. Arthur-Merlin, in which this guy possibly sends an R prime and then an M prime, and then so this is A of X MR. This will be A prime of X R prime M prime. So this is what we want to show. I want to show this transformation. Can I just replace?
Can I use R prime by R?
Can I just use the same R prime? And then can I just use the same R prime and get the proof?
I guess so, because anyways.
No. What do we have?
Always be the same, right?
So we have let's look at in completeness. We have that probability. We have that there exists an R. Here I want there exists a M such that probability over R A X MR is accept is greater than 2/3. And soundness, what I want is for all M, probability over R A X MR is accept should be less than or equal to 1/3. Certainly, if you flip the order of quantifiers, you can show the same thing. This will imply, you can in this one you can flip the order of quant. So this is X belongs to, this is in the case when X belongs to L. Then you have this, X not belongs to L. You have this. So in certainly this case you can flip the quantifiers and you can show if certainly for a particular M, for most R is told that for most R you can actually get the same thing. This is the picture which RP had. So if you draw this picture in which you have, these are the random coins, these are the messages. What are we claiming? There is one message M such that most random coins accept. Now, what do I want to show? I want to show for every random coin, there exists a message. Certainly that is true. That's the completeness. But let's look at the soundness case. Soundness case, we say, no matter which message you choose, most R's should reject. But this need not be true if I flip the quantifiers. It might be true that for most R, if I flip it, actually, I can be able to give you a message that accepts. If flipping it will take completeness to completeness, but it will kill the soundness if you look at it. So what we will do is we'll just boost the error probability. So we can boost the error probability. So amplify to obtain there exists an M such that probability R AX MR equals accept is say greater than or equal to 1 over say 2 m plus 2 l plus 1, where m was of length 0, 1 to the l. And in this case, you will amplify so that for all m, probability of r, sorry, what I meant was
That be 1 minus
1 minus 1. Greater than or equal to 1 minus 1 over 2 to the l plus 1. And this is probability of AXMR equals accept is less than or equal to 1 over 2 to the l plus 1. So suppose we did this amplification. Now I want to claim, now post the amplification, you can actually swap it. Why? Post the amplification. So suppose x is in L. Then we know that there exists an M such that probability R AXMR equals accept is greater than 1 minus 1 over 2 to the L plus 1. So certainly this implies probability over R AXMR equals accept is greater than or equal to 1 minus 1 over 2 to the L plus 1. That's certainly true. This is in the completeness. This is a completeness. Let's look at the soundness. X not in L. What do we know? We know that for all M, probability over R, AX MR equals accept is at most 1 over 2 to the L plus 1. Now I want to ask.
How are those two statements that you wrote are two different? Like,
Sorry. This statement I had to put in directives.
Yeah.
This is just the fact that the completeness here goes to completeness. That's a trivial statement. If it is true, if there is one M for which no matter which random coins you do it, certainly there is, for every random coins, you can give the same M and it will work. You could have given the same M. The prover could have ignored the random coins and given the same M. With the soundness case, what happens? I want to say, you amplify this. Now I want to ask for all M, what's the probability that AX MR equals accept? This we can write it as 1 minus probability over R. There exists an M such that AX MR accepts. This is certainly less than or equal to 1 minus summation over M probability.
AXMR equal to reject, right?
No, I'm writing AXMR equals accept. I want to say that is bounded above by
No,
1/3.
probability that R for all it accepts is equal to that. I'm not sure.
Which one? You're asking about this statement?
Yeah, this, yeah. How is that true?
Oh yeah, this you're right. It's not equal to this.
Okay.
No. What am I saying? Okay. But this we already knew. This is exactly 1 minus summation M, 1 over 2 to the L plus 1. Therefore, this is less than or equal to 1 minus 2 to the L times. Am I messing up something over here? This is equal to half. So you get this gap. See, once you do the amplification, then you can swap the quantifier. Then the point is soundness was important. The point is, okay, the point out here, could you swap directly M and this one? You could give this. The point is, he could give an M prime which is tailor made to the particular R prime. Depending on what R prime, he could give an M prime. But the point is, if you have driven the error so low, then even though he could give a tailor made, he's more or less constrained by this factor. Unless you just draw the picture, you will get that this one. This is just a union bound going on over here. Okay. And actually, you can take the same proof, almost the same proof, and get the following. Extend the same proof
Is this like also in like when for perfect sound completeness, would you do the same proof for IP?
What?
On one side, it's closer to 1, right? And on the other, in the soundness, in the completeness argument, the probability is closer to 1, but in the sound
Yes.
thing, it's half. So like, isn't this like the same thing that the 2/3 you could take it to 1 for the completeness thing when it comes to IP that you said? Is
Yeah.
it sort of, can we go in a similar way to prove that?
The soundness make it from half to 0.
No.
Is that your?
From 2/3 you take the completeness to 1,
Yes.
and from 1/3 sort of get it down to half or something, or get it up to
Yeah.
half. Is it the same proof for IP?
I don't follow what you're stating.
So in IP, you said that in IP for the completeness, it was at least 2/3, right? And
Yes, and you can, and there's a proof in which you push it to 1.
get it to 1. So is it the,
Yes.
can we apply this proof?
No, that proof will require that proof. No, that's not the same as this. That's not the same as this. Only pushes it closer and closer to 1. It never, these kind of things will not push. Amplification will push you closer to 1. It will not get you to 1. To get you to 1, you have to do something more. To get you to exactly to 1, and this is going to be on the next problem set to do it. You can extend the same proof to show that any, not just MA, any AMK for any constant K is actually contained in AM1, which is equal to AM. With any constant around AM protocol, you can just get it down all the way to AM. Okay. So let's actually, I'm going to list the properties of Arthur-Merlin proof systems that we saw last time. That we mentioned.
I'm a bit confused as to what you proved in the above statement after getting this half and.
What did I prove? I proved the following. I amplified the randomness. I amplified the error to become so small, and then I swapped. I let so the previous protocol was in which author did not reveal his randomness, but now he reveals the randomness, and then Merlin tells you what the proof is. So this is an MA proof. This is an AM proof. We have shown that any MA proof, if you give me, you can convert it into an AM proof. At the end of this is what I have shown. Because of this, hence MA is contained in AM. Because any such protocol, give me any such protocol, I have converted it to such a protocol.
Find the AM by 2/3 and 1/3, right? So you can you also have to show that you can write down this 1
Okay, so it's possibly let's don't make it to 2/3, let's make it L plus 2. So then this will be L plus 2, and this will be L plus 2. This will be 1/4. So you're in good shape.
Then in the completeness thing, you define it as a 2/3, right?
Yeah, but it's even better. It's 1 minus 1/2 to the L plus 2. It is much better than 2/3.
Yeah, okay. Yeah.
It's far better than 2/3.
Yeah.
I haven't. Okay. It's far better than 2/3. So the properties of AM proof systems. This is something we listed last time. Let's recall these properties. The first of them is P space is contained in AM poly. This was the TQBF proof. It showed that there was a public coins protocol. As Satyajit said, actually what we showed is MA poly. But if it's polynomial rounds, I don't care who starts. So this was done last lecture. What we see as a surprising thing towards the end of today's lecture is IPKN. That is, this is private coins. Is actually contained in AM KN plus 1. So this is public coins. Later today. P for all constants K. That's something I listed just above. For all constants K, AMK is contained in AM1. This AM. And 4, this will be in problem set 4, problem set 5, and then AMK has perfect completeness. I just want to list a couple of corollaries of the following. We saw that graph non-isomorphism was contained in IP2. This was what we had seen the proof. By what? By 2 above, this will be contained in AM4. Sorry, AM3. This is messing all of this up. This is IP1. It was just a one-round protocol. So this will go in AM2, and this will get contained in by 3. This will go back to AM. Okay. We haven't proved either 2 or 3. 2 or 3 is 2 will be proved later in class, and 5 is this one. But let's assume this for now. I want to do a couple of inferences from what we have from these properties already, and then see why these properties are interesting to look. These are just arbitrary properties that are drawn about the Arthur-Merlin proof system. Why are they interesting? But before that, even before that, let's go back to our picture of the complexity classes that we have. Let's find out where we are. So the complexity zoo. Let's draw the zoo. So we had. I'm going to put P at the bottom now. There's L and all of that below, but let's put P at the bottom. Just above P is BPP. Arrows are showing containment, and then you have NP over here, co-NP over here. And now MA is clearly a generalization of NP. And so for the same reasons, co-MA will be a generalization of co-NP. It's just the complementary class. And certainly BPP is contained in MA because it and in co-MA. So BPP is contained in both. Then there's this class AM, which I said contains MA. And therefore there's similarly class co-AM that contains this. And what did we see? MA, we further said it's contained in sigma 2. This is contained in phi 2. Yeah, so this is a picture which we have. So far so good. And but for what did we know further? We further saw that there is sigma 3p, sigma 3p over here in this butterfly of classes, phi 3p. And certainly sigma 2p is, you have these sort of containments. This containment going this way, this containment going this way. But I want to claim that what we have AM is in BPP to the NP by definition almost. Because it's author talking with an NP prover. So it's exactly in BPP to the NP. So there's BPP to the NP, and BPP to the NP is certainly in sigma 3p and phi 3p. You can show that. So this is a picture of the complexity picture that we have right now. We have this picture, and there The NP complete problems and all are sitting over here. Here is the graph. All the NP problems are sitting here. And by our conclusion, what we saw was graph isomorphism, rather graph, did I write graph isomorphism? Graph non-isomorphism. Graph non-isomorphism went and sat over here. This contains graph non-isomorphism, or equivalently, graph isomorphism is sitting over here. Now notice, if graph isomorphism were NP complete, that means co-AM will collapse to NP. Unclear? Let's look at this. Is exactly what I want to ask. So this is a question which we'll now ask. We'll just ask, what happens if co-AM is contained in, if NP is contained in co-AM, or equivalently, co-NP is contained in AM. I want to claim then the hierarchy collapses, PH collapses to AM, and hence is a huge collapse is going to happen. And we already have all the ingredients for the proof of this, is what I want to say. So let's just look at the proof. So I want to look at a proof. Let's look at a sigma 2p statement. A sigma 2p statement looks like there exists some x for all y, p of x. Now, this guy is a co-NP statement.
So that is an AM.
So that is an AM. So in particular, this you can replace it with AM. But this is something like M. That means any L in sigma 2p is actually implies L is in MAM. But MAM, as we saw, because of round reduction, it's contained in AM. This is what I had written over here. This is item 3.
Could you just show the item 3 once again?
Item 3 says AM of any constant number of rounds collapses to AM.
So then it will be MAM, right?
No. Any constant number of rounds collapses to AM. 1 second, I'm going to change place for the class from. You still see me? Everything visible? Yeah. Okay. Good.
Yeah.
Okay. So no. So what was the question over here?
By the way, your charger is not plugged in, or it's not. I mean, it's not on.
Oh boy. 1 second. You can see that better than I can see. Now you say I have bookcase credibility. Fair enough. Okay. So any constant round MAM, whichever way it is, it eventually goes to AM. So this means sigma 2p, that is sigma 2p. Sigma 2p is in AM. But sigma 2p, AM we already saw in this picture of classes. AM is in, by the way, I should have written this. AM is in pi 2p. This we saw it right before. We saw this over here. Where did we see this? So AM is in pi 2p. This part. I can draw two particular pictures in this. So AM is in pi 2p and coam. This picture is horrible to draw, but yeah. So then this is contained in pi 2p and the hierarchy collapses.
Prahladh, the
Yeah.
diagram that you've drawn right now, it gives us CoNP is in CoAM, right?
CoNP is in not CoNP is in coam, yes. But suppose CoNP were actually in AM. That's what I'm. CoNP is in coam is trivial.
Yeah.
By definition, because NP is in AM. NP is in AM. Therefore, CoNP is in coam. But now suppose the other thing happened. CoNP was in AM rather than coam.
Yeah, this is the theorem's assumption. Okay, I got lost.
This is the theorem. This is the theorem's assumption. If you had the theorem's assumption, then I claim the hierarchy collapses.
Yeah.
No, but this is a remarkable theorem which says that
I still didn't get why is MAM a subset of AM?
Anything with constant number of rounds is AM. Collapses to is always contained in AM. MAM is also a constant number of MAM. You can think of it as AM. It's AM with 2 rounds. The first round is a useless round.
Oh, the first round is Merlin sense and then Arthur sense back. Right?
So you can think of it this way. You can think of certainly MAM is contained in AM. You can, because the protocol just ignores the first round of Arthur,
okay. Yeah.
and then it's contained in AM.
Yeah. Okay. Yeah.
So any number of rounds of protocol is contained in AM. So if that remarkable thing which we said, what does this mean? So suppose, so I want to say this actually has a, so what happens? So I want to say what happens is, so now let's look at what happens if graph isomorphism. The graph isomorphism is a problem which we have had in NP for a long while, and we have not been able to prove its NP completeness. Now suppose graph isomorphism is actually NP complete. What would happen because of this? Then for what would you have? You would have GNI. GNI is CoNP complete. But GNI, we already know, is contained in AM. We showed it was in IP1, and then we showed that public coins, private coins, this is in AM2, which is contained in AM1, which is AM. This will tell you that hence CoNP falls into AM and pH collapses. So the corollary of this is the following. If graph isomorphism is NP complete, then pH collapses to sigma 2p. In fact, to AM. And I want us to sort of stare at the statement for a while. The statement actually is a profound statement out here. Graph isomorphism is a problem been in NP for a long while. It's like these classical NP problems. And it's a problem which we failed to sort of prove NP completeness for a long while. Unlike the other things like vertex cover, independent set, SAT, TSP, and all, those where we were able to prove NP completeness. And you could ask, why were we not able to prove NP completeness for this? And this says, if you had proved NP completeness for graph isomorphism, then the hierarchy collapses to the second level. And notice this statement. This statement has nothing to do with interactive proofs or anything. But this whole theory which we built over the last 5 lectures actually gives us a way to understand why we were not able to prove NP completeness of graph isomorphism. Had we proven NP completeness of graph isomorphism a while ago, we would have actually collapsed the polynomial hierarchy, which is a statement we don't believe. And hence, this is the reason why we haven't been able to prove and graph isomorphism was not NP complete. So the reason I just listed out those properties and sort of did these blind calculations as well is to tell you that those properties of AM actually have a very profound impact on our knowledge of various combinatorial optimization problems. There's a reason why we were not able to prove graph isomorphism not being NP complete, and that's because of this. If you had proved it, the hierarchy would have collapsed, and the way we proved this was using this whole interactive machinery of interactive proofs. Okay. By the way, to my knowledge, I know 3 different proofs of this corollary, all of which go via interactive proofs. 3 different proofs of corollary, all using interactive proofs. The first one is the one above. The second one is in the book, Aurora Bara. And the third one, which I know will go into problem set 5. So there will be 3 such proofs, and they seem to be 3 different proofs, but all of which use the machinery of interactive proofs of Arthur-Merlin proof systems. Okay, so let's pause for a while and see any questions. This is an important one, and if you have any questions, let me know.
The proof to the corollary was like so naive in some way. Like
No, but this
it was like, but a very easy result. Like
no, but proof of the corollary is basically the proof of this theorem. But the proof of this theorem is also fairly simple. You just take an sigma 2p statement. Let's look at it. It's a sigma 2p statement. There exists for all. Because co-NP is in AM, the for all can be replaced by an AM. And there exists. So you can give me for any sigma 2p statement, I claim you can give a Arthur-Merlin protocol. Because this exists can be simulated by Merlin. He sends across the proof. There exists X. And now he has a co-NP statement now that the prover, the verifier needs to check. But you already assume the co-NP has AM. Therefore, there's an AM protocol. Now, the verifier can toss some random points, send it across, and then the prover gets it. So you have an MAM protocol for, basically we have shown that there's an MAM protocol. Basically, all of this put together is an MAM protocol for sigma 2p. This is just using the assumption. But now you use the more properties of MAM. MAM is in AM. Therefore, L is in AM. But AM itself is AM is in pi 2p, because AM is randomized followed by existential. Randomized, you can put it as for all exists followed by exists. That becomes a pi 2p statement. So AM is in pi 2p. So you get this entire sequence of response, and that's the full collapse. Let me write this a little more. This one. So co-NP is in AM implies sigma 2p is in MAM. That just follows from assumption, which is in AM. This is round reduction, which is in pi 2p. And that is just almost definition of AM will tell you it's, and the fact that BPP is in sigma 2p will give you pi 2p. Therefore, the hierarchy collapses to the second level, and that second level actually is AM. It's slightly smaller than the second level. Okay. And I'm using both these properties. I'm using, which are the properties I'm using? We are using both these properties. We are using the property that graph nonisomorphism had an AM protocol. The protocol which we gave was an IP protocol. It was a private coins protocol, but I'm using the fact it has an AM protocol. And then the AM protocol, I'm further reducing the number of rounds of the AM protocol to all the way to 1. So I'm using these 2 steps in the proof. Okay.
So this proof is kind of like giving us evidence that graph non-isomorphism is expected to be easier than NP complete problems, right?
So graph isomorphism. It's easier than NP complete problems. It is rather, it doesn't tell you. I do not know what you mean by easier. It cannot be NP complete at what it says. It might be that the case that if it becomes P, it might all. There is no CARP reduction from all of NP to graph isomorphism. We don't expect that to be the case.
And what's the best thing we know about graph isomorphism right now?
So, by the way, a couple of years ago, there was, so one way, of course, how to prove this is to show put graph isomorphism as in P. If you show that, then we haven't yet managed to show that. There was a recent remarkable paper due to Latsi Babai a few years ago, which showed that graph isomorphism has a quasi-polynomial time. It's not an exponential, it is 2 to the power polylog n, where the poly is not is 2 to the power log of some log square n or something. So it's greater than polynomial, but significantly smaller than exponential. Typically, NP-complete problems, we expect them to be completely exponential in running time. This is much smaller than it, but not polynomial yet. It's conceivable that graph isomorphism eventually collapses to P, but we are not yet there. Rather, our algorithmic friends are not yet come there. Yeah, but what we do know is that there's a polylog. So what we do know. Finding your question. So recently, this is actually very recent. It's possibly 2 years ago. Babai in a remarkable work. By the way, this is the same Babai who defined Arthur-Merlin proof systems in 1986. So he's been working on graph isomorphism since 86 till 2016. Graph isomorphism showed that graph isomorphism has a quasi-polynomial polytime algorithm. Okay. So AM has a lot of very nice features about it. We listed a couple of properties which were useful in proving graph isomorphism and about the M, which sort of gave you something about the graph NP completeness of how easy is it to prove NP completeness of graph isomorphism using these properties. What I will do in the remaining half an hour is take one of those properties and try to prove them. I won't have time to prove all the properties. We'll prove one of them. In particular, what we will prove is this. So the rest of the lecture. What we'll show is this result of Goldwasser, Shafi Goldwasser, and Mike Sipser, where they show that public coins equals private coins. And this is actually, the idea is a very simple idea, but if you look at it's a beautiful, on the face of it, if you look at it this way, it seems as if it's completely untrue. How can you come up with a public coins protocol for graph non-isomorphism? Let's look at graph non-isomorphism. Graph non-isomorphism, it was crucial in our protocol. The soundness of the protocol depended on the fact that the verifier was hiding the randomness from the prover. But I'm now going to give an alternate protocol in which the verifier is just going to tell away the randomness and yet be able to, and yet it will be an interactive proof in which it's a public coin protocol, but yet prove to you that the graph is non-isomorphic. Okay. So the theorem which they prove is actually the strong theorem. The theorem that we call the theorem they prove Goldwasser Sipser is IPK is contained in AM K plus 1. A special case of this is the fact that graph non-isomorphism is contained in AM2 protocol. Okay. So what we will show in class is I will only show the graph non-isomorphism part. I will not, but it's exactly the same idea that goes into the whole thing. We'll specialize in the case for graph non-isomorphism and show that there is a public coins protocol rather than a private coins protocol. Okay. So for this, let's recall.
So Prahladh, by the way, like this Sipser Goldwasser protocol is the same thing as this thing?
Same thing as what?
As this theorem above, is it the same?
Yeah, this is the theorem. The theorem of it's this. The Goldwasser. This result is DS or Goldwasser and Sipser.
No, like there was some Goldwasser-Sipser protocol which puts a problem in this AM intersection coem. Is this the same thing, or?
Where did we do this?
No, we didn't do this. Like there is some Sipser Goldwasser protocol, right? It's the same thing.
Not that I know of. I don't know. There is a. I don't know of any other Goldwasser Sipser. There is something which is in AM intersection coem, which is a Goldwasser Goldreich protocol of shortest vector problem, but I do not know.
Okay. Yeah.
So let's recall the private coins, the original private coins protocol for graph non-isomorphism. So once again, what was the setup? There we are given two graphs, G0 and G1. I'm going back to verifier and prover because this is a private coins protocol. And let's assume that the number of vertices in G0 and the number of vertices in G1 both are n. If they are not n, the graphs are obviously non-isomorphic and you didn't have to do anything. And how was this protocol? First, the verifier picked one of the graphs at random, that is picking like a random bit. Then the verifier picked a random permutation of the n vertices. And he sets a h to be, take this graph GB, which he has picked, and permutes them according to this permutation, and then sends h across to the prover. The prover finds C such that GC is isomorphic to h, and sends C across. Verifier accepts if B equals C. Notice, and it is crucial that this was a private coins protocol. Okay. What we now want to do is I want to design a public coins protocol which has the same feature as this protocol. I'm going to use the properties of this protocol to convert it to a public coins protocol. How will we do that? So let's, for instance, let's construct the set yes to be. What are all the set of messages that the verifier could have sent in the first round? The verifier, what is a h? H is something which is either isomorphic to G0 or isomorphic to G1. This is the set of messages, set of possible messages sent by verifier to prover in first message. For starters, I'm going to make an assumption. It won't be clear what this assumption is, but let's assume. Let us assume that both G0 and G1 do not have any automorphisms. What do I mean by that? By the way, G and G0 are labeled graphs. They are labeled graphs 1 to n. An automorphism is a relabeling of the graph in which you get back the same thing. For example, a triangle has automorphisms. You can relabel it. All the cyclic permutations of 1 to 3 are going to, in fact, any permutation of the 3 vertices is going to give you back the same for this one. So I want to assume that it has no relabeling, any relabeling such that the graph is isomorphic to the relabeled graph.
So a square
is not isomorphic. It's identical to the relabeled graph. Let's ignore this assumption for now. We will have to keep this. If I want to claim what if G0 is not isomorphic to G1, what is the size of S? If G0 is isomorphic to G1, what is the size of S? I want to ask these two questions. How large is the set of isomorphic graphs to G0 and G1? If G0 was...
In the first case, it is 2n factorial, right?
The first case, it is 2n factorial. Yes.
And in the next case, it is n factorial, right?
It's n factorial. So it's clear that in the first case, the number of possible messages that the verifier could have sent is 2n factorial if the graphs were non-isomorphic. In the second case, it's n factorial. So what we'll sort of try to say, we won't give an IP protocol. We will give a different protocol in which the prover not says, doesn't tell you, you won't run this protocol. We say in the first case, I'll show you that the number of messages that you could have sent me in the IP protocol is actually a much larger number. So in one case, in the yes case, there's a large number of messages that the prover verifier could have sent. In the no case, there are not a large number of messages. What we'll instead give is now a protocol, a public coins protocol, where the prover convinces that in the graph non-isomorphism protocol, the private coins protocol that we had designed, the number of messages that the verifier could have sent is actually a large guy. It's more like 2n factorial rather than n factorial. He'll show how to do this using public coins. If he does that, then then the verifier will be convinced, yeah, because the number of messages I sent to the first round were 2n factorial, then it has to be the case when the graphs are non-isomorphic. Okay, I had to fix the small assumption that the graphs are this one. So to remove that simplifying assumption, I'll do the following. I will change remove the assumption. To remove the assumption, we will redefine S as follows. Has to be, take it to be H and some phi. So firstly, there exists a B in 0, 1. H is the same thing as before. H is isomorphic to GB. That's just isomorphic to one of the graphs. And phi is in Sn such that phi of H is equal to H. This is not isomorphic. They are identical. That these are, it's automorph. I'm counting it with automorphisms. So pi is an automorphism of the graph H. Want to claim at this point of time, you don't have to go into these details. All I want to say is in this case, you can ensure that this case, in fact, is 2n factorial, and this is n factorial. You have to check what automorphism and all means. You can make a final check. Just believe me for this. The whole point is to show that in one case, the set yes is very large, in the other case, the set yes is very small. This is what. So the observation, all that I want you to take at this point are the following remarks or observations. Is the size of S is different in the yes and no cases. In particular, it is large in the yes case and small in the no case, and there's a gap between the yes and no, and a gap. It's not greater than k and less than k. There's actually a gap and a gap between the two cases. That's all I want you to take from this. How you did this one. And the second thing is membership in S. If somebody says membership in S can be checked with a proof. That if somebody says some SH, some S pi is in, so that is, if I claim H of H pi is in S, how would you give me this proof? You just give me the
B and
you give me B sigma, you give me B and sigma such that sigma GB is equal to H, and you also check that pi H equals H. You check, and all of this can be done. So this is the NP proof. So membership, that's all I want you to take at the end of this. The proof has this feature that in the yes case, there are a lot of random coins, that lot of things, the membership in yes has a large number of things in yes. In the no case, yes has a small set. And any private coins protocol is sort of like this. S will be sort of the accepting random strings in one case, and S will be, if you put yes to be the set of accepting random coins, in the yes case, you're saying there'll be 2/3 of them. In the no case, you'll say there are at most 1/3 of them. So there's a gap, and this is what we'll do it for the general case. But let's just focus on graph non-isomorphism and this particular problem. Are people with me so far?
Yes, yes.
So let's abstract out this problem that we have right now. So there is some universe U. Let's call this universe. This universe is graphs. In this case, it's graphs on n vertices cross Sn, set of permutation. That's the universe which I have. S is some set S over here. And in the yes case, what we know is mod S is greater than or equal to K. Let's define K to be equal to 2n factorial. And in the no case, mod S is less than or equal to K by 2. And furthermore, any h pi in S, this has an NP proof, has a proof. What does the prover want to do? Prover wants to convince via a public coins protocol. That's crucial over here. A public coins protocol that yes is large. If he does that, we are done. Are people with me so far?
Yes, yes. So just one thing, this Sn is the set of all permutations, right? Of the n.
Yeah, Sn is set of permutations. Okay. Yeah, so this will lead us to what I'm going to call the set lower bound protocol. So the input here is M, which describes the universe. So the universe, I'm now going to abstract it out and write as 0, 1 to the power M. Just let's work with some universe of this type. Previously, it was graphs into permutations. Let's just think of them as m-bit strings. Fixed encoding, there's an m-bit string, the universe of this type. And I'm giving you a set S in 0, 1 to the M. But how do I specify? I specify this S specified implicitly. I can't give you S because S can be very large using via an NP oracle. That is, whenever you ask me any element, if the element is in S, I can give you a proof. If the element is not in S, I don't have a proof to prove it to you. So S is specified implicitly.
Prahladh, what was U?
U is the universe. U is the universe over here was graphs cross Sn.
Okay.
So in other words, this can be viewed as 0, 1 to the n square cross 0, 1 to the n log n. Any graph can be written as an n square matrix. I'm viewing it that way. Permutation can be viewed as an n log n string. That one. So the m which I had here is n square plus n log n possible. It's some encoding of the input.
Yeah.
And I'm giving you S, but I'm specifying S in a very implicit fashion via an NP oracle. That is, if somebody the way S is specified is, you can always check whether something is an S by giving you a proof. If there's something is not, I cannot give you a proof that it is not an S. This is how S is specified. And the goal for us is to distinguish these two cases. Distinguish that mod S is greater than or equal to K, or mod S is less than or equal to K. So I also specify the input, I give you a case. So let's look at the picture again. This is the universe, 0, 1 to the M. I give you some S. You need to tell me whether this S is large or small, and you need to give it using public points.
Do you query random points?
How would you do this?
So can you query random points?
You can pick a random point, but the point is, yes, S, you do not know how large or small S is. S could be so small that a random point will almost never lie in S.
So, but if you query like k by 2 plus 1 points, then
yeah, but k is a large number. K is like n factorial. You can't query so many points.
Yeah, okay.
So k some number between 1 and 2 power m. K is some number. So I should have given that also. K is a number between, say, 1 and 2 power m. You can assume you only give multiples of powers of 2, but k is some such number. You want to do this. And the key idea is a thing which we have used over and over again, is to use pairwise independent hash functions. So what you might be surprised, what do I mean by that? So let's just find a small k such that this k is sandwiched between 2 power small k minus 1 and 2 power small k minus 2. I possibly should make one of them strict inequality. Actually, it doesn't matter which one I've done. So let's find such a k. And the idea will be, we'll do the following, and then look at this space 0, 1 to the k. And let's look at hash functions from 0, 1 to the m to 0, 1 to the k. So this hash function is mapping this whole space.
Can you just change the notation of small k? It's getting a bit confusing with the capital.
Okay. Okay. Let me call it L. Find L such that 2 power L minus 2, 2 power L minus 1. Zero power L, 0 power L. Okay. That's going to be the idea. So I'm going to hash the whole universe 0 into 1 power m into 0 into 1 power L. In one case, S is a large size set. The other case, S is a small size set. So what do you expect? What do you expect? That is, if S is a small size set, notice S is now significantly smaller than k by 2. And k is roughly the size of this universe. K is the size of this universe. S is significant. The small set S is significantly smaller than k by 2. Most guys here will not have a pre-image in S. If S is small, most guys in 0, 1 to the power L will not have a pre-image back in S. But if S is large, then because of pairwise independence, most of them get mapped uniquely to different guys. Most guys here will have a pre-image. And that's going to be the basis of our this one. So is the idea clear? So you're going to hash the whole universe to 0, 1 to the power L. My video went off again. It has been on for a while. So I'm going to hash the entire universe 0, 1 power m to 0, 1 power L. And 0, 1 power L is comparable to the size k that we were targeting for. Now, if S is large, because of pairwise independent, most of S gets mapped uniquely, and most guys in 0, 1 to the power L will have a pre-image. If S is small, even if they all got mapped uniquely, the fraction of 0, 1 to the power k that they can cover is only like k by 2, which is much, much smaller. Most guys will not have a pre-image. So this suggests the following very natural protocol.
A pre-image in S.
You want a pre-image in S.
Yeah.
So what the key observation which I want to say is if S is large, most elements in 0, 1 to the L have a pre-image in S. If this is 1 and 2, if S is small, most elements do not have a pre-image. So this suggests the following very natural protocol. There's Arthur, there's Merlin,
So
and
do
they are
you
given.
check the image of so do you sort of check the pre-image of S/S? No, nothing.
So what's going to happen is S is specified implicitly. This is the input, and then K and M are also specified to you. So what does Author do? Author does the first step. He picks H randomly from this family of hash functions. So H is a pairwise independent family of hash functions from 0, 1 to the M to 0, 1 to the L. We saw this already. He first picks a random element of the hash function. Then he's going to pick a random element in the range 0, 1 to the L. And he sends both across. He sends both H and Y to the prover. Now the prover needs to send a pre-image. What does that mean?
H inverse Y.
So he has this,
like whether H inverse Y is an S or no.
so he's going to send me an S. So firstly, I need to check that H of S is equal. So verifier accepts. Verifier accepts. If firstly H of S has to be equal to pi. Sorry, H of S has to be equal to Y. But how does he know S is in capital S? He will also give me a proof that S is in S. So he'll give a member that proof. Let's call it something. And so he's going to check this and the proof that S is in S. He'll check this and then accept. If both these pass, he accepts.
And we know that the proof isn't big if S is an S.
Yeah. So if the prover is ever going to pick a S in S, there is a short proof, and the prover will give me that short proof along with this. This is the protocol. Notice this is a public coin protocol because why is it public coins? Because Author has completely revealed out in the open what he's tossed. Okay. And the thing is, at this point of time, it should be okay. They have the calculations to do. We'll do it in 5 minutes or so. But it should be clear in the S case, most elements in capital S will have a pre-image. So most elements in 0, 1 to the L will have a pre-image. Therefore, with high probability, the prover will be able to find. The other case, invariably, Y will not have a pre-image, so you will not be able to send you such a thing. There'll be of course, the verifier Author could have been unlucky and picked a Y which had a pre-image, but the probability of that happening is going to be small. That's all we're going to show. So we need to prove we'll have to prove completeness and soundness. So actually soundness is the easier fact. We need to show that if mod S is less than or equal to K by 2, then probability over H and Y, there exists an S in S such that HS is equal to Y. We want to show that this is small, say less than 1/4. This I want to say is actually In fact, we'll show that in fact, we'll show that for every h, going from 0, 1, fix a h. What is the probability over y such that there exists a s in s? Hs is equal to y. This is certainly at most summation s in s, probability Hs equals y, union bound. But this one we saw, this is exactly 1 over 2 to the power L. So this is less than or equal to k by 2 by 2 power L. And k itself was chosen to be less than 2 power L minus 1. So the 2 power L minus 1 by 2 power L, that gives you 1/4. This is just the fact that the pre-image does not have too many. The size of S itself is so small, therefore most guys in it don't have a pre-image in S. This is the easy direction. Let's do the other direction too, completeness. Understood? If mod S is greater than or equal to k, then probability over h and y, there exists a s such that hs equals y is greater than or equal to, I'll figure out what this is. We will add that once we do the calculations. Okay. In fact, here we will show the other direction. In fact, the proof for this, in fact, we'll show that. Let's in fact fix a y in 0, 1 to the L, and let's ask what's the probability over h. There exists an s in S such that hs equals y. Notice I can't use I need to lower bound this quantity, so I can't use union bound. Union bound is I'll put an upper bound, but I can do the second step of the inclusion exclusion. I can write the summation s in S, probability hs equals y, randomness of h, minus s prime are distinct, s not equal to s prime, probability hs equals hs prime equals y. And possibly this is the I should write this as
probably s less than s prime or something.
Yeah, yes, s prime, s not equal to this is just over pairs of, let me write it as pairs of s prime so that s not equal to s prime. So the set.
Why is this a lower bound? Is it like this is equality, right? Or no?
No. Equality. You will have to put then h. This is like you have to write what's the probability that there exists a guy. Then the probability that two guys conflict. Then 3, and then 4. It's an inclusion exclusion. Union bound is the first step of the inclusion exclusion. This is the second step. So each time the thing gives you, what are these called? These are Born. What inequalities are these called? Bonfellini or some inequality. Basically, yeah. So,
what is it called?
I'll just write it on chat. So I think it's called Bonferroni inequality.
Yeah, Bonferroni inequality.
The generalization of union bound to.
Yeah. So what is this? This is just exactly size of S to the power 2 power K, 2 power L, minus size of S choose 2 to the power 1 over 2 power 2L. Because of this is because of pairwise independence. By the way, why is the protocol succinct? The protocol is succinct because we use an efficient pairwise, and you can use some. We know that there are short descriptions of H. We can do that. Therefore, the protocol is sufficient. It's not an arbitrary one. Now, why is this calculation is something I haven't done? This one I want to claim. I want to claim this is greater than. So here we'll be using the fact that mod S is greater than or equal to 2 power L minus 2.
Yeah. S was utmost k by 2. So, oh, sorry, this is the completeness case. Okay. So S is at least k. So it is at least 2 to the L minus 2. Yeah.
You just pull out mod S by 2 power L and.
Yes, is at least k, which is at least 2 power L minus 2. I'll pull out mod S by 2 power L. Okay. Then I get 1 minus mod S minus 1 by 2 power L. Is that right?
Yeah, and the second term you can bound by a smaller quantity, right? Or rather, what you can.
How do you do this? The first term I'll bound by 2 power L. The first term is 1 by, is what is 1 by 4. Is that what I have? But I'm already doomed if I have that, no?
No, I think you should have half probably.
This is sort of similar to what we did in Valiant-Vazirani also.
No, this is exactly the same idea. This is exactly the same idea. Why do you have half?
Sorry, mod S is at least as large as.
2 power L minus 2.
Wasn't it 2 power L minus? So can you go up? I mean, like I don't remember the choice of L.
The L was chosen to be. This is the choice of L.
Okay. Yeah.
Okay, and we know mod S.
This is some x into 1 minus x, where x is between 0 1, right?
It's sort of like that. It's almost like that. X into 1 minus x. So what will that be?
Wait, is that upper bounded by 1/4 or lower bounded?
Yeah, that will only give an upper bound of 1/4.
Oh, okay.
But on the other hand, we know that S by 2 power L is no. Is actually that upper bound is got exactly when S by 2 power L is half. But this is like 1/4. S by 2 power L is more like 1/4. Therefore, the upper bound will go. It will be much away from 1/4.
So sorry, just 1 second. We want a lower bound here. So
Yeah.
suppose you replace the inner one, the mod S by mod S minus 1 by 2 power L by a mod S by 2 power L.
Yes.
We are still in the right direction, right?
Yes.
Okay. Because I'm subtracting more. Okay. So now what do I know about mod S by 2 power L? I know mod S by 2 power L is at least 1/4. Is that what I know?
Yes, from this.
It's at least 1/4. Let's actually choose.
Actually, that doesn't help, right? I mean, like
no. Let's fix an S star subset of S such that S star is exactly of size k. And this quantity, I'm going to write it as this is greater than or equal to probability there exists S in S star HS equals 1. So make it 1/4.
Sure. Okay. This is also something we did similar in the Valiant-Vazirani type calculation.
Yeah. So now you'll get it's not going to be 1/4. It's going to be significantly away from 1/4.
I'm actually still.
I don't see. No, this is like x into 1 minus x.
Okay.
So this it has to be.
So currently you've chosen mod S to be mod S by 2 power L is equal to 1/4.
But how can it ever be greater than 1/4? It can never be greater than 1/4. Did I mess up with my question?
I mean, it somehow feels like the factor of 2 gap that you had where it just seems to have gone missing. Because on one hand, we only had mod S by 2 power L. Wasn't that right?
Okay.
Is it because because of the when we took the combination S star 2, we forgot a 2 over there on the denominator?
Yeah. There's a 2 over here. Sorry.
Sorry, what?
There's a 2. There's an extra 2 over here.
S
Doesn't
choose
matter,
2.
right? The first term itself you're saying is 1/4. That's the best you can say. This is anyway some quantity less than 1.
Quantity less than 1. That is true. All I want to claim at this point is this quantity. No, let me write it this way. This quantity is 3 by 4 times mod S star by 2 power L. Let me state it this way. 3 by 4 times mod L. This is greater than 3 by 4 times K by 2 power L in this case. And the other case, it was, so to this case, it was less than or equal to K by 2 to the L plus 1. And I want to say now I have a gap. In this case, it's K by 4. It's K by 2 to the L plus 1. And here it have 3 by 4 to the these numbers. So since 3 by 4.
Sorry, how did you get 3 by 4 mod S star by 2 power L?
This quantity is at most 3/4. Is at lower bounded by 3/4.
I think it's 7 by 8, not 3 by 4.
That's even better for me then.
Oh, I
This
see.
quantity is 3/4. Therefore, in one case I get 3/4. So what do I get? I get the following. I get the following. In the yes case, probability of acceptance is greater than 3/4 times K by 2 power L. In the no case, I get probability of acceptance is at most half times K by 2 power L. There's a gap between the two. Now I can amplify the gap. That's all. That's all I want. There's a gap between the two. I should have done this a little more careful. In the yes case, so these two are two separated numbers. There's a constant gap between them, and hence you can now go ahead and amplify this. Yeah, the calculations are a bit this one about it, but the main point is you can use pairwise independence to sort of say that if you have a set whose access you have by a membership oracle, in the yes case, you can show that the actual set size is large by just a public coins protocol. So what the proof Merlin is trying to show, he's not trying to run the original interactive proof protocol for graph nonisomorphism. He's showing the original interactive proof protocol had a lot of random coins that would have caused the verifier to accept. That's what he's showing. And he's showing a lower bound on this point. And in general, the general proof from IP to AM goes the same way. That is, Merlin will there'll be a public coins protocol, and Merlin will convince the author that there's a lot of random coins that convince the original private coins protocol to accept. And there's a gap between the number of random coins that cause it to accept and the number in the yes case and the no case. In this gap, you will use the set lower bound protocol. It's going to be the same protocol which we'll do. You'll have to do it a little more cleverly along with round by round, and that's it. Okay. Sorry, I was very hasty with this. Let me just, because this is going to be the last part of one. Let me conclude. What did we get out of this? Out of this, what we have is the following feature. So graph non-isomorphism, which was in IP1, actually has gone into Arthur-Merlin 1. I didn't even have to, this was just a one round, back and forth, one round protocol. We got this is the end of. Okay. Yeah, so we had this picture of interactive proofs. Interactive proofs was nice to understand what you can do with the help of a prover, but it not only gave you that, it gave you something meaningful for something which did not involve interactive proofs at all. In particular, I talked about why we have not been able to prove NP completeness. But the original reason why interactive proofs were defined were actually defined. They were defined independently by two different groups. Babai had originally defined it to understand actually graph non-isomorphism. That was the reason why he defined Arthur-Merlin. And then there was an independent group led by Shafi Goldwasser, Silvio Micali, and Charlie Rakoff, who were trying to understand more cryptographic protocols and something called zero knowledge. And this is what we'll spend in the next lecture onwards. Ram Prasad will talk about zero knowledge proof systems of the interactive proofs which we have talked about. The next will be on zero knowledge proof systems. Yeah. I thought I'll spend some time to motivate what this is, but I think Ram Prasad will. I'm already way past. Any questions? Okay.